my screen sharing. We'll see if that all works. Okay, can we all see that? Perfect. Okay.
Yeah, it looks great.
Excellent. Excellent. Yes, so I'm thrilled to be here sharing with you some of the work we've been doing within the Simpeg and sort of broader open source software communities that I've been involved in. Just a note here, if you would like to follow along with the slides, and I do have some links for resources and things like that. I've got a bit.ly link here where you can follow along. And afterwards, if you have questions that I perhaps miss in the Q&A, you're welcome to leave a comment on the slides and I will try and get back to you there. Perfect. So let's see if this advances. There we go. So you heard a bit about my background. And so just to give you a bit of context, and this will shape some of the presentation that I'm sharing with you today. As mentioned, my thesis work was really on geophysical inversions. And so I've done a lot with electromagnetics, some in the context of mining and in groundwater and natural resources. So a lot of simulation, so building up 3D solvers for Maxwell's equations, for example, and then trying to work with those data to understand subsurface electrical conductivity in those applications. That led to my involvement in an open source software project called Simpeg, where we are working on developing open source tools for simulation and inversion in geophysics. And then on top of that, we built a suite of open educational resources in a project called geosci.xyz. And so it's a collection of textbooks that range from sort of undergraduate applied geophysics up to much more more advanced electromagnetic methods. And these include both the web-based textbook, but also interactive simulations that are built in Jupyter notebooks. And that really led to a lot of my involvement, which is where I am currently, working on a project called Jupyter Meets the Earth with the group at UC-Berkeley. We also have collaborators at NCAR. And what we're doing with this project is really trying to advance both Jupyter technologies in their application to geoscience research. And so it's a collaborative project between folks who are software developers and geoscientists working together to try and advance these tools as they serve geoscientists. So as I mentioned, some of the problems that I've been looking at and have focused a lot of my work on are imaging the subsurface. And so to give you a sampling of perhaps a few important problems where we might need to try and understand and map and characterize subsurface physical properties, it could be anything from natural resources like minerals. It's becoming more and more important as we're looking at high power or high efficiency batteries, solar panels. So as we continue to sort of transition off of hydrocarbons, it's going to continue to be an important area of development. Groundwater is particularly relevant. We see this in California in the agricultural sector, where we draw a lot of water resources and need to understand what the groundwater tables are like. Also in tons of areas around the world currently, as populations continue to grow, water is a very valuable resource that we need to understand. Alternative energy sources like geothermal and so on. And so you see there's a large variety of problems where we need to characterize the subsurface. And so with geophysical data, I'm sure everyone's seen an image along these lines in introductory courses. And so what we're trying to do is we've got models of the Earth and we have data. And what we're trying to do is if we have, for example, a model where we've got expected physical properties of the subsurface, we want to be able to simulate what we expect a survey to give us in terms of data. And so this can help with survey design and things like that. Also make sure that we're actually able to detect what we are interested in. But in general, we're actually most interested in going the other way, is that we've collected some data over the Earth and we want to go and then estimate a physical property model of the subsurface. So there's some important differences between each of these two directions. The forward problem is well posed. We have, if we've described and discretized the Earth, there's one unique solution to what those data look like. Whereas going the other way, this is a non-unique problem, ill-posed problem, where we've got, we need to include things like regularization and a priori assumptions and geologic information to be able to constrain what this model of the Earth looks like. So if we talk about what we actually need in terms of computational tools, there's really two major components. Is we need to be able to predict data. So if we build up a voxelized model of the Earth, break up the world into cubes and assign physical properties to each of those, we need to be able to simulate, for example, these are the DC resistivity equations. over that in order to predict data. And then inversion, the way we're going to approach it is through optimization. And so what we're going to do is try and design an objective function where we want to fit those data. So find a model that fits the data. And then there's some regularization term that allows us to impose assumptions like smoothness or geologic information. And we solve this through optimization. And so that means we need to be able to iteratively solve these numerical equations and also compute things like sensitivities and derivatives. And so we've been building Simpeg in order to do this. So it's an open source project where we've got a suite of different geophysical methods. You can see I've listed a number of them here. So we've got potential fields, gravity and magnetics, DC resistivity, induced polarization, electromagnetics, both frequency and time domain, as well as what might be of particular interest to some folks here is natural source methods, so like magnetotellurics, as well as fluid flow. And our goal here has really been to design a common framework that can work with all of these data. And so that if we want to start looking at things like joint inversion, or if we just want to be simply operating in a software ecosystem that is consistent and has sort of consistent naming conventions and things like this between the different methods, that's really what we've been aiming for. So to give you a flavor of what some of the things are that you can do with Simpeg, so the first thing we want to do is define our mesh, which is how we're going to discretize the world. So we define a mesh, and so here, this HX and HY, these are just cell widths in each direction. So you can see this is 3 units wide, this is 2, that's just following this. We build up a tensor mesh, and so if folks are familiar with Python, this is written in Python. This is now an object. So it's object-oriented programming, and so you can do things with that object. There are methods. So for example, we can plot the grid and we can see what the geometry looks like. So the geometry are actually then properties. So we have things like the locations of the cell centers, the edges and faces. So we've got that geometry. But the other thing that we get with that is then we can also build up our discrete differential operators. And so, for example, if we want to solve something like electromagnetics, we need to have a discrete representation of the curl. And that's just based on the geometry of the mesh. And so we get that right away. So now we want to solve some equations. So here we've got our continuous DC resistivity equations. We can go ahead and discretize those. So we use a finite volume approach. And so each of these then is a matrix that we're just going to multiply together. So this gives us our system matrix. And what's quite nice about working in something like Python, where we've got object-oriented code, is we can really actually, and we've sort of thought through and tried to design Simpeg this way, so that the math that you write down really looks like the code and is reflective of the code that you've written. So here we've got the divergence, the representation of the inner product of conductivity and the gradient. And so this is our discrete representation of the system matrix for DC resistivity. Then we want to go ahead and invert that because we want to solve for potentials. And as anyone who's done numerical computing knows, we never actually explicitly solve and compute A inverse. But we can create something that looks like and acts like A inverse, so that when we actually perform this operation here, it does that solve for us. But this could be using an efficient solver. One of the things that you'll notice that's quite nice when we talk about sort of modular object-oriented code is there's actually nothing specific here about which type of mesh I'm using. So in the previous slide, I showed you, for example, a tensor mesh, but maybe we've got a more advanced octree or sort of a adaptive mesh. As long as it has these operators, we can go ahead and plug that in and reuse this code. And so as advances are made in that mesh class, and in the types of meshes that we use, we can go ahead and use the same machinery and same code to solve those equations. So the next piece then is going and solving the inverse problem. And so there's two main components to that. Is we're going to define it, as I mentioned, as an optimization problem. So we want a part where we're going to fit our data within some uncertainties, and we capture the uncertainties in this WD matrix. But then we also impose some regularization. And so this is a standard sort of L2 regularization, which gives you smooth results. But there's a lot of research and interest in looking at different norms. So norms that perhaps promote compact structures in your inversion. And so if you design software in a modular way, then each of these pieces can be swapped out, and you can experiment with different approaches here. And then again, the other thing that you'll notice is in this case, there's nothing specific about which physical set of equations we're working with. As long as we've got the mechanisms to estimate data and sensitivities, all of the same optimization machinery and same regularization machinery can be plugged in for any of the problems that we work with. So to give you just a bit of a flavor of what some folks are doing with Simpeg, I've compiled a few examples from the community. So this is a mineral exploration example led by Dominique Fournier. He's with Mira Geosciences in Vancouver. And so he's been looking at large-scale magnetic inversions and using adaptive meshes. And so this octree mesh work was led by Joe Capriotti, who's now at the University of British Columbia. And so with these adaptive meshes, what has been done for the mag problem is we actually break up this large problem into a whole bunch of subsets, so smaller problems that each can be solved much faster. And so by breaking this up, we can parallelize over very large areas and very large areas. The other interesting thing that Dom's been working on is looking at magnetic vector inversions. And so in this case, instead of just inverting for susceptibility, also accounting for in some places where we have remnant magnetization or permanent magnetization, trying to recover that direction. And that can give us some interesting insights about tectonic history. This work is led by Sagi Kang. So he's currently at Stanford University looking at groundwater challenges in California. And so they've collected a whole bunch of airborne electromagnetic data, which is sensitive to electrical conductivity, which can tell us about where we have clay layers, which would be conductive, versus aquifers with fresh water, which would be more resistive. And so in this case, he's been asking questions and examining, can we actually draw conclusions from inversion about connectivity between aquifers? So if we've got an upper aquifer and perhaps a deeper aquifer, how you manage those changes if they are connected versus not. And so he's been looking at inversion work, different regularizations, as well as different geostatistical techniques to go from resistivity to lithologies. Thibaut Astic, he's been looking at joint inversions. So this example here is inverting together both gravity and magnetic data with petrophysical information. And so if there's been well bores drilled, or we have some insights as to about which rock types we expect to observe and what their physical properties are, those are then pieces of information that we can try and include actually in the inverse problem. And so with that, then instead of just inverting each of these independently and then having to sort of interpret and draw your own conclusions and your own geologic interpretations, we can actually invert those together to build up a geologic model through the inversion process. And then recently, we've deployed these in a different context for actually a Geoscientists Without Borders project that was sponsored by, so it's through the SEG, the Society of Exploration Geophysics, where a number of folks pictured down here. So Doug, Kevin, Max, and Devin all went down to Myanmar and actually collected DC resistivity data with local geoscientists and engineers. And we deployed Jupyter notebooks that include examples that run Simpeg code so that they could go ahead and actually work with these data and try and locate and spot locations where you could actually drill water wells into deeper aquifers there, because the shallow aquifers tend to dry up in the dry season. So I've showed you some of the code and some of the capabilities and things that folks in the community are doing with this code. But I think a lot of our motivation comes from both, yes, wanting to build useful tools and tools that serve researchers, but also sort of in a recognition that a lot of the problems that we are starting to be working on and trying to solve are multidisciplinary. And they require input from multiple people and multiple domains in order to solve a problem. And so what this image is showing is we got time on the x-axis, and anything that diverges away from this zero line here is effort. And you can see, in a sense, there's two different styles of effort that come to play when we look at these types of computational problems. There's the algorithmic problem. And so, for example, if you're implementing a joint inversion, there's a lot of moving pieces. And so you need to have software engineering experience and numerical experience to be able to actually go ahead and implement that. But then to actually go and interpret, and when we're really trying to answer some of these applied problems, like managing groundwater, like assessing examples in mineral exploration and trying to understand the tectonic and geologic history, you have to have a lot of knowledge from different domains. And I think it starts to become pretty clear that no one person and no one tool set can actually span this gap on its own. And so beyond just being a community resource, a software resource for folks who work with geophysical data, what we've really been working towards and trying to promote is actually that this also be a collaborative community where knowledge and new ideas that are developed in one domain can be transferred to others. And so it really is, it's both the code, but it's also the community. And so there's the code that you can access and learn about through the Simpeg website. But there's also a number of communication channels and ways to get in touch and get involved. And so this is an image of some of the current contributors who are involved. And it's really exciting to see that there's folks at different universities. So yes, we started at UBC, but now there's contributors from Colorado School of Mines, Stanford, Houston, TU Delft, as well as industry contributors from DS Geophysical and Mirror Geosciences. And so it's been exciting to see that by collaborating and building community around a common resource, we've been benefiting from really having a space where we can all interact and exchange new ideas, and where different people's priorities push the code forward in different ways. So a lot of the research examples really require flexibility of the code base. But folks who are working on industry often need efficiency and speed. And so they've been working and pushing very hard on making those sorts of improvements in the code base as well. And so what are some of the things that we do to actually enable this process to come together, both for the code and the community? So we've been seeing, and we've employed a lot of software engineering practices. So things like versioning the code, tracking issues, having very comprehensive test suites. But also the peer review of work. This is something we do in science when we publish papers, but it's equally valid and important when folks suggest changes at the level of an implementation. So that's talking about sort of how do we actually manage the software, but as I've mentioned, it's people who are involved and people who write that software. And so it's equally important to have different mechanisms for communication and for working together. So we've got weekly meetings that we host on Zoom and record and post up on YouTube. So if there are folks who want to follow along or hear about what we're up to, you can access all that through the website. We've got a chat on Slack, which is very sort of real-time communication, easy to send files back and forth and just have a discussion. And then we've also got a discourse forum where folks can come and post questions, and we can work through and collaborate on ideas there together. Another thing that we've been working on that I mentioned early on is geosci.xyz. And so this actually builds on top of Simpeg to deploy educational resources. And so we've got textbooks on applied geophysics. It's at an undergraduate level, as well as advanced electromagnetics, and a number of courses that have been run with these resources. And this leverages a lot of the tools in the open source community for both deploying textbooks, but also for embedding and using code in them, which is quite interesting, is so that if you decide that you want to go a level deeper, rather than just reading the book, you can actually download the code and start to play with it. And so, as I mentioned, that Simpeg is one sort of set of tools in the open source ecosystem, but it really is the Python ecosystem is a very broad ecosystem that serves a lot of different use cases and a lot of different researchers. And so, what's really interesting about being part of this ecosystem is that we can actually go and benefit and build upon advances that are made in other communities. So, for example, with Jupyter. Jupyter provides us a framework for interactive computing. If folks have questions about that, please feel free to let me know. I'm happy to answer in a bit more detail afterwards. There's tools like Binder, which allow actually, if you've defined your notebook or notebooks, if you put those in a repository and you define what your software dependencies are in a standard file, Binder will actually build that software environment for you and drop you in online on the cloud so that you can actually go ahead and run those notebooks online. And so it's a really exciting demonstration of distributing reproducible work. As if you've got the notebook and the environment that you need, you can hand that link to anyone in the world and they can go ahead and start playing with it. Of particular importance to some of the work that we've been doing in Simpeg is Dask, and this is a tool for parallel computing. And it was in very early stages when we first started the Simpeg work, but now it's quite an advanced tool. And so it's something that we're able to incorporate and build upon and have the code parallelized much more easily than we would have done on our own. And then, of course, as we see machine learning entering so many different fields, being able to leverage tools like scikit-learn, or as well as some of the deep learning frameworks, and being able to interoperate with those, because we're building on sort of this common core of tools within the ecosystem, makes it easier to translate information and ideas back and forth. So as I mentioned, what is Jupyter? So Jupyter gives us an interactive computing environment. You can combine code and text and widgets and things like that, all in one document that you can then share. And one exciting thing that's been happening, or one exciting advancement in the community, is the Jupyter Hub project. So I'm sure many folks have run Jupyter on your laptop. But what Jupyter Hub is actually working towards or is able to do is actually launch Jupyter on shared infrastructure. So for example, on the cloud or on HPC centers, so that you can really scale up the work that you've been doing from your local machine onto these high performance machines, but still have the same interface and that same look and feel, and not have to sort of translate all of your research code into a batch script that can be run on any HPC center. The Pangeo community, and we've been building on this in the Jupyter Meets the Earth project, is really an exciting effort that is pushing forward both on the technology and on the geoscience side of things. And they've really pushed forward both on the Jupyter, Dask, and X-Array projects. So Dask, as I mentioned, does parallelization. X-Array does data models and numerics. I'll show you just a quick example here of some of the capabilities that they've been working on advancing. So you can see that, zoom in on a map, we can see some bars here moving at the bottom, and then it sort of, we get that high resolution image served to us. So what's the big deal? You do this every day on your phone. Well, that was 100 gigs of Landsat 8 data over Washington State. And so you can see that, you know, being able to actually process and crunch through all of that with almost real-time interactivity, just both the same interactions that you expect on, you know, data that's served to us every day, but with your scientific data, I think is quite an exciting example. So how does this sort of come back to the initial questions that I was asking with respect to sort of Simpeg and simulations and inversions in geophysics? We again have these two components that we're working on, is both the code. So we're working on incorporating some of the advancements that have been really pushed on by the Pangeo community, like Dask and X-Array. And in particular, the space where we're really working on advancing right now is the 3D electromagnetics and magnetotellurics. And so if those problems are, if they're of interest to you, please feel free to get in touch. We'd be happy to collaborate, hear your ideas, and see if there's some solutions we can help you with. But also on the community side of things, is that you know, the code is of no use if it's not used by people. And so we've been putting a lot of effort into documentation, getting the tutorials up and running, and some forums, as well as connecting with new contributors and trying to make a habit of reaching out and providing a smooth onboarding process there. As well as conversations on governance and decision making. So, you know, when you start a small project, this can be fairly fluid, but as projects start to get larger, this is an extremely important conversation to have, is how decisions are made when you have a bunch of people who are collaborating in a space. So I just put this in here. If you are curious to find out about any more of these projects, there's a handful of useful links, and as I mentioned, feel free to reach out. And with that, I will wrap up and say thank you, and also highlight folks from each of these communities, from the Simpeg community, the Jupiter, and the Pangeo communities, whose work have definitely made all of these efforts possible.
Great, thank you so much, Lindsey. We do have a question, and if you have a question for Lindsey, please type it into the Q&A box. So Manuel says, great talk. Has there been any prior joint inversion that includes seismic data in Simpeg, particularly for lithospheric scale research?
So actually, you'll notice in the list of capabilities of Simpeg, seismic is actually currently not one of them. And so it's interesting because that just hasn't been a focus of the researchers who've been involved so far. So we don't actually have any examples like that. But there are some excellent open source tools that would be really exciting to work to interoperate with. So OBSPI, for example, does a lot of work in sort of global seismology. And so if you had a use case where you were interested in combining some of that capability with Simpeg, that would be one I'd be very keen to find out about and see if there's something that we could support you with.
Great. There was a kind of a question in the chat box, but Lindsey, I don't know if you want to do this, but there was just a question if they can access the slides, especially given all the resources that you put at the end. We'd be happy to take your slides if you'd like and put them on the IRIS website. But if you would just like us, to take the couple of slides and not the rest of it, that's fine too. But yeah, IRIS would be happy to host any of the slides or materials with those resources. Absolutely.
For sure. And actually, if you want access to it right now, this bit.ly link should take you there.
Oh, great. Okay, awesome. There you have it. So I don't see any other questions that have come in so far, but that's okay. Please type your questions into the Q&A box and Lindsey can answer them as Michael is speaking. I'm also going to put into the chat box instead of the Q&A box just the survey that I was speaking about real quick, and that helps us to inform future webinars and how you enjoyed today. In the meantime, I'm going to transition over to Michael's talk. And feel free to get set up while I'm introducing you. So our second presenter today is Dr. Michael Olsen. He is the College of Engineering Dean's Professor in the School of Civil and Construction Engineering at Oregon State University. He obtained BS and MS degrees in civil engineering from the University of Utah and a PhD in structural engineering from the University of California, San Diego. At OSU, he teaches courses in geomatics topics such as 3D laser scanning and imaging, digital terrain modeling, and geographic information systems. He is also the editor-in-chief for the ASCE Journal of Surveying Engineering, as well as the president of the Surveying and Geomatics Educators Society. His current areas of research include geomatics technologies, algorithm development, 3D visualization, rapid reconnaissance, and geospatial hazard mapping, monitoring, and analysis. He serves as the technical director for the NSF Natural Hazards Research Infrastructure Rapid Facility, which provides investigators with equipment, software, and support services needed to collect, process, and analyze perishable data from natural hazards events. He is also the director of the Cascadia Lifelines program, which conducts research that allows Oregon's lifeline providers to implement value and cost-informed decisions to mitigate damage to the Pacific Northwest infrastructure as the result of Cascadia subduction zone earthquakes. He is also a co-developer of the Oregon Hazards Explorer for Lifelines program called OHELP, which is a powerful web GIS platform designed for the engineering community and hosts a wide range of hazard maps for Cascadia subduction zone earthquakes, including ground acceleration, liquefaction, landslides, and more. So without further ado, here's Dr. Olsen to talk about From Big to Small, You Can Do It All, efficient approaches to analyze rockfall activity from point clouds. Take it away.
All right, thank you, Danielle. That was good. Appreciate the introduction there. And I was thinking you have such an animated voice, maybe I should have you give the whole presentation too. Anyway, thanks, Lindsey, for your excellent presentation. It's going to be a tough act to follow. A lot of really cool stuff that your group's doing there. So I'm going to talk a lot about some work that we're doing for rockfall assessments using LiDAR technology, as well as unmanned aircraft systems photogrammetric methods to analyze different impacts of rockfalls and some interesting geologic observations that we've made in this process. The work, as you can see on this title slide, there are a lot of different people I've had the privilege to collaborate with at the University of Washington, Joseph Wortman leading a group there, as well as GNS Science with Chris Matthey and Garth Archibald, as well as Oregon DOT and the University of Alaska Fairbanks. So a lot of, just want to recognize that this work comes from a lot of people beyond myself. Okay, so the kind of the motivation for this work, we have a lot of highways, particularly in the Pacific Northwest of the United States, but you can find these everywhere, where we've got a lot of cut slopes that were cut back a long time ago. They're basically well past their design life, and we've got a lot of rockfall problems along these different slopes. So there's these very long isolated highways. In a lot of cases, these are the path from one place to another, and they're really the only route to connect one community to another. And there's a lot of safety and mobility concerns if these roads get closed. You know, then it presents a lot of problems for these communities to be isolated, especially in situations like post-earthquakes and so on. So a lot of departments of transportation are looking at ways that they can be more proactive in managing these slopes. So rather than waiting for all the rocks to come down, let's identify where the problem areas are and let's start mitigating those. And let's implement some techniques like this barrier wall that you see here to help protect the highway. Now, the challenge is we have limited personnel. We don't have a lot of money. There's a lot of these areas that have issues. And so we got to figure out how to prioritize these in terms of a long-term plan and asset management framework. The problem becomes very compounded when we throw in the seismic aspect. So this is some LiDAR data collected after the 2016 Kaikoura earthquake in New Zealand along their Highway 1. And as you can see, there was a lot of rockfall problems as well as landslides that shut this highway corridor down. There's physically no way you could pass it, and so on. So it creates a lot of problems in these post-seismic settings of having these routes to be able to get people out to evacuate. Some places they had to evacuate people via helicopter because there was simply no way to get in and out via road. This is just looking the opposite direction in one of the tunnels with the train tracks that were dislodged as a result of the seismic movements there. All right, so traditionally, how do we do this? One of the common approaches used in practice is what we call the rockfall hazard rating system. And so in this case, you look for signs of weathering and other signals on the slope. It's a very costly process. You got to send somebody out in the field. It's very coarse. They look across a pretty large area at a time and kind of make up, you know, they come up with the numbers based off their expert judgment, but it's still a very subjective process. We also have detailed assessments where you send somebody up on the slope on wires and they're crawling the slope. That's obviously a very costly approach to do it because you're paying somebody to be in a very hazardous position. So their rates are, you know, very expensive. There's a lot of liability associated with that. Again, it's subjective. They're seeing the slope very, very close, but they can't really see the slope as a whole from their perspective. So they can maybe get detail on a few things, but it's very hard to kind of understand what's going on at that level. And then it's also obviously a very unsafe situation. And so the question is LiDAR technology or unmanned aircraft systems, could they be a solution? These are very high detail, high accuracy technologies. They're rapid acquisition techniques. There's challenges though, particularly in the data processing side of how do we go from this point cloud into information that describes the slope. So, you know, where's that magic button that we can get out our assessment of whether the rock slope's precarious or not. And so with this research that we've been doing for the Pacific Transportation Research Center, we've been working on developing some tools for this. So we go out in the field, we collect data, a lot of different platforms that we use. In this case, it's a wagon mounted scanner. So we can collect a scan in a couple minutes and move on to the next spot and collect the corridor pretty efficiently at a very high resolution. Go through georeference the data. Then we need to clean out vegetation that grows on the slope, model it, and then we do some different types of analyses. And that's kind of what I'll talk about today in the presentation. So data acquisition, there's all sorts of different platforms depending on whether we, what level of accuracy we want to achieve and what we want to accomplish in terms of the assessment of the slope. We can also use mobile LiDAR technology as a more efficient way to cover very large corridors to narrow this down, and then maybe terrestrial in the areas of higher interest. So one of the aspects that we did is we looked at different technologies, and we looked at using structure from motion, multi-view stereophotogrammetry, compared with terrestrial laser scanning. And so these are some results of some different comparisons. And kind of the overall conclusion that we came up with as a result of it is, as long as you are using good survey control, and so you set some survey control, in this case we used a total station, you could achieve some pretty similar results with structure from motion, multi-view stereophotogrammetric approaches as you would with doing terrestrial laser scanning, with the benefit of being able to have the speed and the vantage points of the unmanned aircraft system. So typically we're seeing results that were within about 6 to 8 centimeters between the surfaces. And so you can get very good results. Now, I think that the challenge is a lot of people kind of see the UAS as a low-cost technique, and they go out and collect a lot of data, but don't apply any survey control or very limited survey control. And in those cases, the models break down, and you can have a lot of different challenges. In terms of resolution, on the right-hand side, kind of shows some examples of resolution. You know, one advantage to a UAS technology is that you get this more uniform distribution of points across the surface, which is better for modeling compared to terrestrial laser scanning. You know, the base of the cliff, this area in red that you see in the bottom right, there's a lot of dense data, but then the areas in blue on the upper sections of the slope have very limited data. And that can be very problematic when trying to create a model across the area. So they definitely each have their ups and downs. No matter which technique we do, we don't capture quite everything, and so we have to do some interpolation. And so this is an approach using thin plate splines that we found to work pretty well. This is not a case of, in these magentas, this isn't somebody shot a bunch of paintballs at the cliff, although I'll have to tell you a story about that at some other point of trying to use paintballs as reference targets on the slope. But in this case, these magenta splotches are areas that we've applied the thin plate spline to interpolate the surface so that we can do change assessment and different volume calculations and so on throughout it. And so the nice thing about this particular surface filling technique is it's a very smooth technique that kind of follows the curvature and the shape of the rock surface. So once we go through and we do this, we collect the data and we create these models. The next thing we can do is we can start classifying the surface. So I mentioned earlier, we apply typically in practice the rockfall hazard rating system, looking across very large sections of the slope. In this case, we developed a technique called the rockfall activity index, where we can compute at 5 centimeter increments across the slope. So very high detail, we can look and see what's going on. And so the idea behind this approach is we compute morphological characteristics. So we look at a very localized slope vector, and we also look at roughness across different window sizes or different spatial scales, because that gives us information about what's kind of present in terms of the rock, how the weathering processes are happening. Those are all indicative of, you know, roughness or rugosity in the surface of the slope. So we take the point cloud, and at each point, spaced at 5 centimeters, we compute the slope. If there's very high slopes, so greater than 90 degrees, meaning that the surface is pointing downward, that tells us that that is an overhang, and we can classify it into a shallow overhang or a very heavy cantilever overhang. If it's less than that, then we look at the roughness in a 35 centimeter window. If it's not very rough, then that tells us that it's probably either talus deposit at the shallower slopes or intact rock, because it's the smoother rock surfaces. If it is rough, then we can look at it and we can make some computations based off the spacing of the discontinuities and how much fragmentation is going on the rock. And so that gives us an idea of kind of what the activity rates or failure rates would be associated with each of these categories. We do this classification based off that. So the flow chart's one thing. I think it's sometimes easy just to see an example. So this is a rock slope up in Alaska on the Glen Highway. And we have kind of different pullout sections to show just different processes happening on the cliff surface. So in item B, we have talus deposit. So you can see the surface is smoother. It's finer grained material deposited at the base. And so that's how we're able to use slope and roughness is one way to classify that. In section C, you can see there's a lot of discontinuities. There's a lot of fragmentation going on with the rock surface and a lot more variability in it. And then at item D is where you can see there's overhanging blocks. And each one of those have different impacts of, you know, if they were to fall and different likelihoods associated with how often they fell and the potential implications that they fall. Obviously, the overhangs lead to much more precarious situations. So when we go through and apply the flow chart, we can classify the slopes. This is a slope in Oregon in Eddyville along a new highway realignment that was opened up a few years ago. And we can then color code it based off the different observations. So the dark blue is talus deposits down at the base, and then the red are the overhanging sections, and then the light green is what's classified as intact rocks. And you can see that the bedding plains in this case, the Eddyville is what's called the Tyee Formation. And so it's a mix of sandstone with these clay silt inner seams in between that just create these sliding plains that weather really quickly and fell. So what happens is those receive really quickly. It leads to overhanging of the sandstone blocks, and then those sandstone blocks fell and come down in bigger chunks. And so we're able to capture those with the rockfall activity index classification, identify where those overhangs are on the surface. And then the next thing we do is we look at what sort of failure rate we have associated with each one of these ray classes. And we can compute a score that's based off the energy that would be released if different sections of the cliff felled. And so it looks at what the likelihood of felling is and then what the impact is. So a rock falling from the top of the cliff is going to have much more energy than a rock falling from, a meter on the cliff, because it's going to have more time to fall. And so we can compute that score along 1 meter increments along the slope. That's what you see in the plot at the bottom. And that tells us which sections of the slope are going to be the more hazardous and precarious areas of the slope that have more energy potential associated with them. So this is just an example, again, going back to the comparison of the structure from motion. We can make some comparisons between the UAS and structure from motion data and the LiDAR data. One thing we noted is that the UAS tended to smooth the data out, and that's a lot in the computer vision algorithms of how it creates the dense point cloud. It does a lot more interpolation, which inherently leads to a smoother surface. But in the end, it did a reasonable job of working with the ray system in either type of platform. The other thing is, as we collect multiple epochs of data, we can start capturing information on where these rockfall clusters are happening at. And so we can take the difference model that you see in part B, the absolute or the signed distance between the two surfaces, get an idea what the magnitude of change looks like, but then we can run a connected components algorithm and identify each kind of chunk of rock that comes down. And so you can see all the kind of splotches across the cliff in the upper section. So just kind of zoom in. These are individual rock clusters that between the two epochs have felled. And once we have this information, we've now identified these individual failures, and we can produce magnitude frequency curves. And so on the x-axis, we have the volume of material coming down, and on the y-axis is where we have the normalized number of rockfalls per day per square meter. And kind of the idea behind these magnitude frequency curves is they give us a way to relate the hazard from one site to another, as well as look at the distribution of material coming down. So it's generally, bigger rock falls happen less frequently compared to the smaller kind of day-to-day rock falls. And so it gives us a nice quantitative way that we can look at this. The scaling coefficient, we'll talk a little bit about this in terms of seismic, is kind of what dictates how high or low this is and dictates the hazard between the sites. So now we'll jump over, we went to Alaska, Oregon, now we're going to jump down to New Zealand and talk a little bit about the Canterbury earthquake sequence and some implications in terms of rockfall. We could talk the whole time about the Canterbury earthquake sequence, so much happened there, but there is basically a short story. There were a lot of earthquakes that happened in a very short period of time from one another, and kind of happened in the sequence between 2010, 2011, although there were some other major earthquakes that happened in 2014 and so on. If you followed the earthquake, there was a lot of discussion on liquefaction. City of Christchurch, a lot of large areas liquefied. One of the areas that didn't quite receive as much attention were the rock slope failures that happened. There were a lot of houses damaged from rock slopes, and had the earthquake happened at night instead of the day, then the rock falls would have been a major leading cause of death in the earthquake. But most of these earthquakes happened during the day, so people weren't at home, and so that fortunately prevented a lot of loss of life from these rock falls. So GNS Science in New Zealand did a lot of detailed mapping of where these rockfall runout locations were in the Port Hills of New Zealand, and then associate them with different events and catalog those. This just kind of gives you some examples of the proximity of the houses to the rock slopes and the amount of material that came down. So in the image in the upper right, you can see a lot of shipping containers to protect the highway from kind of the continued rockfall that happened after the earthquake. And GNS Science collected a lot of repeat laser scans during this time period. So we were able to take this data and analyze and look at the patterns of what happened, as well as in these kind of following earthquake events. And so this again shows the clustering results for each one. So part A is after an earthquake that happened in early March 2011. And kind of showing the sections that had happened, but this was doesn't include the pre-earthquake survey. So it just includes 2 surveys spaced a couple months apart, and showing that there were still some pretty sizable events in that time. Between May 2011 and June 2011, a large earthquake hit on June 13th, 2011. The PGA was 3.7 meters per second, and you can see a big portion of the cliff in blue here came down, and then there are a lot of other failures in other locations. And then during kind of the next period, there was another kind of smaller earthquake that happened, additional material came down, and so on. Because they were going out and scanning this earthquake frequently in both seismic times as well as non-seismic times, we're able to evaluate kind of the long-term trends with that and look at it with time. So we're able to develop our magnitude frequency curves using the approaches we talked about earlier. And then we can plot those changes in that scaling coefficient with time after each earthquake event that happened. And what's interesting is you can see this kind of clear decay trend that happens with time after the earthquake. So what this was telling them is that we need to be prepared after an earthquake for increased rockfall activity for some time after. The material's been really fractured and damaged, and so when you get storms through, the impacts on rockfall become much more severe. We also looked at the activity rate, and so how often things were felling across the surface, and related that to the peak ground acceleration that was seen, as well as how that activity rate changes with time. And then the failure depth, or how large into the surface those failures tended to be. Again, there's a correlation with peak ground acceleration, and as well as time after earthquake. So the time really soon after the earthquake, bigger chunks were falling down for some time after the earthquake, and then it went back down to smaller chunks after that. So we could take that information and we could apply these scale factors to the RAISE system we came up earlier, and then use some scenario events. So in this case, we took some from Oregon, applied it to these, and then we can take that same RAISE score we showed earlier, and we can scale it up based off the earthquake. These are different magnitude scenario events that could happen, and we can see how that rockfall activity would be expected to increase as a result of the earthquake, depending on the scenario earthquake of interest. We can also then create plots with time, so we get an idea of what point is that slope going to return back to its kind of more normal situation. In some cases, it's hundreds of days to years before it returns, depending on the configuration of the slope. So this is very helpful for departments of transportation that need to allocate increased resources to clearing the road. So they need to know kind of when those rockfalls are going to happen. As part of this, we packaged up a software product called Rambo. It's basically the rockfall morphological big data optimizer, kind of a mouthful there, but has a lot of these kind of different tools that we're in the process of doing some beta testing with, and hopefully ultimately kind of expanding and getting it out there as a product that people can use. So a lot of observations have come from this work. The rockfall activity index is something that lets us both look really localized at the slope and see the processes that are going on and the morphological indicators, as well as kind of on the broader sections of highway to identify which sites are the most significant. With the magnitude frequency curves, we could see a lot of the effects of which sites were more hazardous and which ones we would expect to have higher levels of rockfall activity. And also saw clear seismic trends associated with that. And so these tools give us a great way to quantify risk along highways, and be able to kind of give us more quantitative methods that are consistent, compared to, say, the rockfall hazard rating system, where I may go up and come up with one set of scores, somebody else goes up and they have a different set of scores, and it's really hard to make sense of those associated with that. And so this gives us some great tools as kind of a starting point to start managing these, to keep the highways safe and open in these kind of emergency situations. And so with that, I'd like to acknowledge a lot of different funding sources and collaborators that worked on this project, and would be happy to entertain some questions.
Great, thank you so much. We did get a question Okay, so make sure everybody that you're using the Q&A, because it's kind of hard to read in the chat box, but I'm going to try my best. So it seems like you need to use interpolation in your work. The person who's asked this question just wants to know what interpolation you may have used, to see also too if you compare different interpolation techniques to see which works best.
Yeah, that's a great question. I mean, that's always kind of the challenge is, you know, do you use interpolation, and then if so, which technique to do? So we published a paper a couple years ago that looked at the impact on the magnitude frequency curves, depending on whether you used interpolation to fill in those data gaps or whether you didn't. You know, and there's definitely certain components where, depending on the rockfall hazards and how big the rock chunks were, where that interpolation makes a difference. And so we've generally kind of done it both ways, where we'll do the process without any interpolation, and then with interpolation, just to make sure that that things don't disagree too much and that we're not over interpolating. We generally avoid interpolating very large areas, because you can get a lot of false positives that way. Also, when we do that clustering approach, we keep track of whether the baseline surface or the reference, or sorry, the new surface, whether or not holes were filled, and we can weight those differently. So if something's based off of more interpolation, then we don't use those, you know, in the actual development of the magnitude frequency curves, whereas something where we've got kind of pure scan data. For rock slopes, the thin plate spline method over a localized area tends to work really well, because it follows kind of that curvature of the slope, compared to something like a Delaunay triangulation or inverse distance weighted and those kind of things. The big challenge with thin plate spline, though, is you have to apply it over a very small window at a time, because it's computationally very intensive, just given the matrix math with it.
Great. Siddharth asks, apart from the frequency of earthquakes in New Zealand, was there any other reason why you selected New Zealand as a site of interest? Have you thought of any other sites for testing?
That's a great question. I mean, one of the main reasons why we used New Zealand was GNS Science in New Zealand was already collecting the data. Having laser scan data, you know, most places you may have it for just a couple epochs. New Zealand, you had a lot of earthquakes that happened at one point in time, but you also had a very dense set of laser scans collected over very kind of short time periods after. So it's kind of a unique data set in terms of that. We also have our other sites in Alaska that we've been studying for years. And so there was recently the Anchorage, Alaska earthquake that happened in 2018, November 2018. And so we've got a really good baseline set of scans before, and we've also done some scans after. One of the challenges with the Anchorage is our sites are in areas where the peak ground acceleration was about 0.1, 0.15, which is where you don't quite see as much of these effects. You know, it kind of needs to get up to be about 0.2 G or higher, where you see those longer term time decay ones. But definitely, you know, we're interested in kind of seeing these trends and how they hold up across the globe.
Great. Lynn asks, can the point cloud data detect rock types?
So that's a great question. We've done a little bit of research in this area. We don't quite have an approach there. I think like with the morphological characteristics, that helps give kind of one indicator to at least kind of generally identify things like, say, schist, where it's just very fragmented and broken. That's one classifier that you could use. The other is with LiDAR, you get an intensity information, which is that return signal strength. And you can use that to make some estimations after you apply some corrections of what the reflectance of the material is. And that's one thing that you can kind of start doing that. There are researchers, say at the University of Houston and Queens, that have been using hyperspectral in conjunction with the LiDAR data, and have found that to be very effective for detecting different types of rock classifications. But they're, you know, generally limits. You know, you may be able to detect like sandstone from schist and other things like that, but you know, beyond kind of those basic categorizations, it can be very challenging with that.
Great, thank you. So there is one more question for you, Michael, and I know Lindsey did a great job of answering questions in the Q&A box, written questions, but if there are any more questions for either Lindsey or for Mike, please enter them into the Q&A box, and I'll let Lindsey kind of have a minute to wrap up in a second as well. Eric asks to you, Mike, have you done any comparisons with ground-based synthetic aperture radar that measures displacement of surface materials?
That's a great question, and the short answer is no, I haven't directly done it. It's something we wanted to do. We had a proposal into NSF at one point to do it that unfortunately wasn't funded, to take a ground-based system and couple it with a LiDAR system and kind of get the benefit of both worlds. You know, ground-based radar has a lot of strengths in terms of the speed at which you can acquire data, the frequency that you can get it, but you also have very high accuracy with the ground-based radar system within that line of sight. But the limitation to a ground-based radar system is the resolution. You know, your quote unquote pixel size, not quite the right term, but kind of that footprint size is much larger in ground-based radar. So kind of the thoughts were is you could take LiDAR data that has very high resolution and merge that to kind of make some inferences with the ground-based radar to do that. There are DOTs that do have permanent ground-based radar systems that they put out on some very precarious slopes as kind of a monitoring system. It's used a lot in mining technology as well. So it's a very good technology for this application.
Great. Lindsey, do you want to join us? Is there anything else that you would like to chime in with your talk, or anything that you'd like to answer live?
Sure. I got a great question from Jonathan. He asked about, so let me just read this. It's hard to do two things at once.
Yeah.
He said, I'm excited to see solid earth geophysics adopt and share cloud resources. Are you aware of any existing public solid earth data sets in the cloud that researchers can use to gain experience using these resources? And I think this is a great question, and actually, I don't know of many offhand. So I did put a link in the chat for the Pangeo catalog, or sorry, in the Q&A for the Pangeo catalog. And it's mostly fluid earth. So there's a lot of climate data sets, hydro data sets. They've really made a concerted effort to put data on the cloud. So I guess what I would like to prompt with Jonathan's question is actually to feel free to reach out to the Pangeo community. They have a discourse page that's meant to just be a public forum to chat and discuss things. And I think it would be great to see the solid earth community, you know, make a bit of a push to actually start to get some more of these data sets out there and available so that folks can actually start getting familiar with these tools and resources.
Great, thank you so much. And Michael, I saw that you answered one of the questions, the last remaining question in the chat, so I appreciate, or in the Q&A box. Really trying to use the Q&A because it's got this great functionality rather than the chat. Are there any last words that either one of you has for us? Anything parting that you'd like to tell us?
Say thanks for coming and putting up, listening to us talk. Definitely a lot of exciting tools out there, and it's interesting to see how these technologies evolve year to year. So thanks for coming.
Absolutely. Well, thank you so much, both of you, for your time and being able to present to us today. I just wanted to say and thank UNAVCO and specifically Beth Pratt-Satola for organizing the GAGE SAGE workshop and for their suggestion to bring these plenary sessions online into Zoom. It's new for IRIS to do this, but we're happy to do it. The next IRIS webinar, so we're done with our GAGE SAGE workshop plenaries, and also the SIGs took place in August. So our next IRIS webinar will take place at 2 p.m. Eastern on November 19th. It's also a Thursday. We will hear from Dr. Andrea Linus from the USGS in Golden, Colorado, and she'll be talking on improving earthquake rate models for seismic hazard forecasts. So we look forward to seeing you then. All right, take care, everybody. Have a great rest of your day. And thanks, Lindsey and Michael. Thank you so much. All right, bye.
Thank you, Danielle, for running this. Thanks.
Of course, thank you. All right, take care. Bye.